Today, it's my pleasure to introduce our speaker, Professor Lorenzo Sironi. Lorenzo is a professor at Columbia University, where he's been since 2016, prior to which he was a Hubble Fellow at Harvard, and then prior to that, he was a PhD student right here. So we're welcoming him back today. He's a winner of numerous awards, including the 2019 Sloan Fellowship, and he is a renowned expert on high-energy astrophysics and high-energy plasma physics, and on shocks and on turbulence and on black holes and on neutron stars and on particle acceleration and on cosmic rays. And as if any further proof were needed that Lorenzo lives his life on the edge, today he's going to tell us about reconnection-powered emission at the boundaries of black hole jets. So please welcome Lorenzo Sironi.
Thank you very much. It's a great pleasure to be back. This place brings back many joyful memories during my PhD. It's especially nice to see many familiar faces, many collaborators that I shared my life with when I was here, and for many projects that have continued over the years. I was going to say that it's especially pleasant to be back in such a nice summer day, but I'm not sure whether we want to joke on that. So what I would like to discuss today is how our understanding of the life of jet boundaries has improved over the last few years. And it's really meant to focus on them and understand how much of a lot of the phenomenology that comes out of black holes and their environments could be attributed to the jet boundaries themselves. I have this buzzword reconnection in my title. I will be defining it just now in the words of Russell Kalsrud, a local presence here at his 90th birthday party, which I attended here in Princeton. He said, Fermi told me to study reconnection about 70 years ago. So it's going to be like a simple PhD topic. And here we are after 70 years, and we still don't understand it. But it's not true. Wikipedia understands it. Reconnection is a process of merging blue and red magnetic field lines of opposite polarity. They're meeting at the center where they're losing their, if you want, political identity in this sheet of electric current, where the overall macroscopic topology of the magnetic field changes due to microscopic plasma effects, indeed localized in this sheet of intense current. In the process, a lot of energy from the magnetic field is liberated, and that's why reconnection may be, and often is, an interesting channel for powering emission. Reconnection is not a peculiarity of high-energy astrophysical systems. It's actually happening very close to us. This is a realization, if you want, of reconnection happening in the solar corona. You have twisting of foot points of magnetic field loops. They open up very often in dramatic ways, producing coronal mass ejections that affect our space weather. Even closer to us, in the Earth's magnetosphere, this is an artist's depiction of the interaction of the solar wind here with the dipolar field of the Earth. You saw that snapping of the magnetic field lines. This is induced by that rearrangement of the topology, reconnection. It's happening on the day side, facing the sun, and it's happening on the night side, opposite to the direction where the solar wind is coming from. So it's really a well-known, widespread phenomenon that has some peculiarity for high-energy astrophysics. And what is that peculiarity? Everything is encoded in this parameter that will come back over and over in my talk. I will call it magnetization. It's the ratio of the magnetic energy density to the rest mass energy density of the plasma. So it says how much the magnetic fields are as compared, how much stronger or weaker the magnetic fields are as compared to the rest mass of the plasma itself. Lab experiments, including some that are very local, are in the regime of magnetization much less than unity, same as the near-Earth, near-Sun environments. On the other hand, many astrophysical systems are in this peculiar regime in which the magnetization can be much larger than unity. Equivalently, the Alfvén speed, the speed at which hydromagnetic waves can propagate, can approach the speed of light. And this is, if you want, in a nutshell, the peculiarity of high-energy astrophysical systems in terms of how much the magnetic energy is as compared to the rest mass. The next couple of slides will be useful to set up a little bit of jargon with reconnection-related topics, so please bear with me. This is the same movie that you have seen before, and we are now focusing, and for the rest of the talk, we will be focusing on the astrophysically peculiar regime of very high magnetization, or equivalently, as I said, Alfvén speed of order of the speed of light. The basic magnetic geometry is characterized by a reconnecting field, blue and red, opposite direction, coming into the center with some velocity of inflow that I'm going to call V in. In addition to that, you have the possibility, and very often the occurrence, of a magnetic field that is sticking out of the page. This is what I'm going to call guide magnetic field. It's uniform, it's not alternating, so it does not enjoy the pleasure of dissipation, unlike the reconnecting magnetic field. The plasma flows into the layer, as this movie illustrates, together with the magnetic field lines at a typical velocity that is of order 0.1 of the Alfvén speed. But we said that for relativistic conditions, the Alfvén speed is over the speed of light. So the flow of the plasma into the layer is happening at 10% of the speed of light. There is a lot of research and study being done on why this is 10%. If Matthew Goodbrag is in the audience, he actually had significant advances on that. So ask him, don't ask me. The other way to phrase it is that the rate at which the magnetic field is being dissipated is very high. It's 0.1 of the speed of light. It's not really a rate, it's a velocity. And in fact, when we talk about reconnection rate, we actually mean reconnection velocity. So keep this in mind. The inflow velocity is 0.1 of the speed of light. Flow comes in, magnetized into the reconnection region. Where does the energy that is potentially dissipated go? Part of that goes in the outflowing gas, the outflowing plasma. It's being advected out by the release of the tension force of the magnetic field lines. Part of that goes into heating the plasma. Part of that goes into accelerating some particles far out of thermal equilibrium and creating non-thermal power laws. A power law distribution, this is again a little bit of jargon, is a distribution that in log of the particle energy, log of the number of particles is a straight line. I think most of us know about that. Why particles can be accelerated by reconnection? Because you do have an electric field. Electric field is great for particle acceleration, and reconnection is able to provide an electric field that is 0.1, this is again where this number is for relativistic conditions, of the magnetic field. So you have an electric field that is as strong as 10% of your magnetic field. Very unlikely you can do much better, which means reconnection is close to be one of the best particle accelerators we have in our universe. And we'll use that fact. So we want to understand reconnection physics beyond what this simple cartoon sketch is giving us. And for that, we need to go to numerical simulations. And specifically, since we're interested in the trajectories of individual particles, the tool to go to is the particle in cell method, which I really think I should not be describing here. This is the place where the field of plasma astrophysics with kinetic tools was born, or at least brought to useful fruition. But let me just spend a few words on that. It's a fundamental method of plasma physics. It relies on Lorentz force, solving the Lorentz force and Maxwell's equations. With the Lorentz force, you push your charged particles. The charged particles are contributing electric currents, and the currents are used to solve for the electric and the magnetic fields of Maxwell's equations, and so on and so forth. The fields are used to push the particles, so on and so forth. It needs to capture plasma scales. Specifically, the characteristic length scale is the so-called plasma skin depth, 10 to the 5 centimeters for a density of 1 particles per cc. The characteristic time scale is the inverse of the plasma frequency, 10 to the minus 5 seconds for a density of 1 particles per cc. So by looking at these numbers, you would immediately realize how small they are as compared to typical astrophysical length and time scales. And this is often the case, which is why we need to be very careful in extrapolating results to realistic astrophysical length and time scales. I will show one example in the Bacall lunch in which we can do peak simulations on realistic scales because nature gave us a beautiful laboratory to do that. But few exceptions exist to this rule, very few. So what does reconnection look like in a particle in cell fully kinetic description? This is a prototypical case. The magnetization is 10, meaning 10 times more energy than in the magnetic field than in the rest mass of the particles. The magnetic field is flipping above and below the midplane. And you see its evolution. It started at the center here because the way we set up the problem, it will advect out of the open boundaries. What you should notice is the constant formation of density structures in a very active, hierarchical way. They grow from small scales to larger scales. They can merge with each other. These are called plasmoids or magnetic islands or flux ropes. They're a byproduct, a natural byproduct of the dynamics of reconnection in a wide variety of systems, definitely not a peculiarity of high-energy astrophysical systems. Reconnection 101 just creates these structures. But of course, we can go beyond that. We can not only know about the flow dynamics, which this movie is illustrating, but we can go a little deeper or much deeper into the physics of non-thermal particles. Yes, Marcus, go ahead.
The threshold that sigma greater than or equal to 1 makes it a relativistic reconnection?
I like to think it that way. So it's really a statement about the Alfvén speed. So anything for which sigma is above unity will bring your Alfvén speed close to the speed of light, and that's what I would categorize as a relativistic regime of reconnection. There are some interesting cases that are in between, in which the ion magnetization normalized to the ion rest mass energy is lower than unity, but the electron magnetization normalized to the electron rest mass energy is way above unity. And this regime is called trans-relativistic, and whether you want to flag it as non-relativistic or relativistic, it depends on the species we're looking at, the dynamics of the species you're looking at. It's a good question. So what can we do further? We can understand how reconnection accelerates particles. And the next few slides will summarize the progress that we have been achieving in the last few years in our understanding of how particles are accelerated in relativistic reconnection. I will flag the people that the various types of works have been done with. I won't spend time introducing them, but it's good to show faces in case you recognize them. Let me give you the punchline first. Reconnection makes broken power laws. So I introduced the power law before. It's a straight line in log space. It can be cast in a formula like this. This is the number of particles differentially their Lorentz factor, going to the Lorentz factor to the minus p. And p is the power law slope of the distribution. There is a break happening at a few times the magnetization in Lorentz factor. The Lorentz factor a few times the magnetization is where this break occurs. The physics below the break, I'm going to call injection. This is what controls the very early stages of energization. If a particle comes in to the reconnection system, the first episode of acceleration is what I would call injection and controls the low energy part of the distribution. Here the slope is as hard as -1. Above the break energy, the slope is roughly independent of the magnetization. I'm summarizing in one slide all of the results of, I would say, 5 to 10 years of peak simulations. And the slope is around -2. It steepens going to roughly -2. You might think that this break is not at significant energies. The magnetization in typical astrophysical systems does not much exceed unity. Yet it's good to keep in mind which species you want to cast the spectrum of. And in particular, for electrons, as I anticipated before in answering Marcus's question, the relevant parameter is the electron magnetization, which is defined as the magnetic energy density to the electron rest mass energy, which is a factor of 1836 larger than the equivalent ion magnetization, which means that if the overall magnetization of the flow, which is controlled by ions, is about unity or 10, your electrons at the break will immediately get to Lorentz factors that are of order 10 to the 3, 10 to the 4. So even the injection stage is capable of producing ultra-relativistic electrons, and so it's worth being investigated. The next few slides I will focus on one aspect, the injection, and then on the other aspect, and I will elucidate the physics that is controlling the two parts of the distribution. So injection part. And the key ingredient here is the fact that reconnection acceleration in this energy range cannot proceed if not because of non-ideal electric fields. In ideal magnetohydrodynamic, the electric field can always be written as minus velocity crossed with the magnetic field. And the interesting regions for allowing particles to be energized in the early stages of acceleration in reconnection have non-ideal fields where this condition is broken. This can be declined in two ways. Both are sufficient conditions for non-ideal fields. Clearly, this condition is violated if you have an electric field locally that is larger than a magnetic field. You have no velocity that can produce an electric field larger than a magnetic field. The velocity needs to be larger than the speed of light, and then we can talk about it. Or the electric field has a component parallel to the magnetic field. This is what I'm calling E parallel. Clearly, this expression does not allow for a component of the electric field parallel to the magnetic field. So these are both sufficient conditions. It turns out one is relevant for weak guide fields. Remember, the guide field is that component sticking out of the plane that does not enjoy or suffer dissipation. The E parallel is the relevant condition. The presence of E parallel is the relevant conditions for a strong guide field. So they kind of exist or are important in different regimes of the parameter space. This is one demonstration of why. Yes, go ahead, Elliot. Actually, I should have said this at the beginning. Questions are welcome at any time. I promised. Yes. Go ahead, Elliot. Yes. Excellent point. So the criterion here knows about the reconnection rate. So I define as strong, and you can so like formally. It's a couple of lines of algebra, but you can formally show that this condition on E parallel requires the field near the region where the alternating field is annihilating to be mostly out of plane. And that's a statement about how big is this region that's controlled by the reconnection rate. So I would say weak is less than 0.1 of the alternating field, and large in this context is larger than 0.1 of that. So this is showing you that that condition is indeed important. In the case of zero guide field, E larger than B regions are the ones driving the early stages of particle acceleration. I'm showing here three representative particles: yellow, red, orange. The small dots are a bunch of other particles that I'm following as they are processed by the reconnection layer. These vertical dashed lines in their energy plot, this is the Lorentz factor as a function of time, indicate times in which the particles are seeing an electric field larger than the local magnetic field. So let's let the movie go. Let's look at the red particle first. About now is the time when the particle is encountering an E larger than B region. You can see that its energy shoots up 3 orders of magnitude in kinetic energy. So fast episode of acceleration associated with a particle seeing a region of E larger than B. Same is happening for the orange particle a little bit later on. Let's see if I can synchronize it well as well. The orange particle about now, it's located in between these two merging plasmoids, sees a region of E larger than B, gets energized by an order of magnitude, it brings it to non-thermal energies. The yellow particle, on the other hand, does not have a vertical dashed line. That's because it never encountered E larger than B regions, and its energy stays relatively small. So the capability for a particle to be experiencing this first episode of acceleration hugely depends on where it is, whether it is in the right place at the right time, which in this context means to interact with non-ideal field components. It's the first message for the first part of the energy distribution. The second part of the energy distribution is controlled by completely different physics, and this is where 3D made a revolution. We have been running for a long time 2D simulations because that's what we could run, but the 3D physics here is bringing qualitative and quantitative different results. This is a 3D simulation, 2 different slices. This is the slice along the field. This is the alternating magnetic field. And now the field is in and out of the page for the slice on the right. So it's the same simulation, still no guide field. There is no uniform component of the guide field. And we're just looking at it from 2 different slices. And there will be this particle that it's evolving, and we'll see how it's moving over time. So for some time, the particle is trapped in a magnetic structure here, a density structure, a plasmoid, magnetic island, those density structures that I revealed at the beginning. And then it starts propagating and nearly unimpeded, moving along the z direction. The z direction here is the direction that 2D is ignoring. So you have translational invariance along z in 2D. And here, instead, the particle is experiencing the variations that you have in the structures of the flow along that direction. There are more quantitative terms, but you can remember this as like the particle is swimming freestyle up and down the reconnection layer. Its motion can just be described by knowing what the large-scale electromagnetic fields are in this configuration. The fact that the magnetic field is flipping its direction is the reason for why the particles can do this half orbit one way, half orbit the other way. The bottom line is that the particle is moving nearly along the direction where the electric field is pointing. The electric field in this slice is actually pointing this way. This is a positron. So the positron is enjoying nearly perfect acceleration. It's moving along the electric field direction with nearly the speed of light. It can be accelerated as fast as one can imagine. And in fact, the energization rate is matching this expectation. The energy gain rate approaches charge, electric field, speed of light, and the electric field is 0.1 of the magnetic field. So the particle can be accelerated at nearly maximal rates. Reconnection is a very valid, very powerful, very fast particle accelerator. And Sasha can tell you more about this 3D aspect of reconnection as well. Yes?
One, to make a distinction between 2D and 3D, are you saying that you don't get gamma as scale in 2D?
That is, so the difference between 2D and 3D is in 2 respects. The slope is indeed much more dependent on the magnetization. And most importantly, this fast energization rate is not achieved. In 2D, the highest energy particles are trapped in plasmoids. Their energy mostly increases because of magnetic moment conservation. The magnetic field increases in a compressing plasmoid. The energy increases as well, but the energy increases as the square root of time. And the particles never leave a plasmoid because they leave along the direction in which the plasmoid no longer exists in z, and it's broken in the z direction.
Suggesting somehow that this reconnection rate of 0.1 is really dependent on your doing the problem in 3D. I'm a little skeptical of this from my intuition on non-relativistic reconnection. It's really wrong. I don't see why the 3D-ness is important in getting to this high reconnection rate. If you have ample evidence to the contrary.
Let me make it maybe a little bit precise. So I'm not stating anything about a difference in reconnection rate. I'm just stating that the voltage that is available for the particles to be accelerated to is only accessible in 3D. In 2D, even though you do have the same electric field, the particles are not able to find themselves in orbits such that they can experience the full voltage, the full potential that reconnection might be available for them, might be giving them, because they're stuck. So they're not.
Follow up, your rate rise is very sharp.
This is the energization rate, right? Yes.
So the dBT is very large. I don't get yet from the simulation why the slope is as large as it is. Is it a theory?
So this part, I am not sure I can explain. This part I can explain. That's because inside the plasmoids in 3D, there is actually very little energization. And this part is exactly what you would expect based on this argument. So am I free? Yeah, so it is a peculiarity of this particle. So if you want, it's a specific realization. What we have seen is definitely this sequence of nearly linear energization and nearly no energization. And what happens in between, okay, we can go a little bit deeper on that. But it is not, I think it's not a universal aspect of all particles. It's definitely a case for this particle, but not a universal aspect. Okay. So we are done with the sort of like physics-based part of my talk. Reconnection is able to accelerate particles. I hope I convinced you that this business of particle energization should be really divided into two parts: the low energy injection part that is controlled by non-ideal fields, and the high energy part which requires 3D breaking of the otherwise 2D translational invariance. So what, yes?
Is there a simple understanding of why you get gamma -2? Now we'll see the explanation.
So there is some understanding. The particles, I mean, we have built a model, but the model still is not a complete understanding. So let me just summarize it in 1 minute. So the model states the following. All of the energization is happening when the particles are not trapped in plasmoids. And that's a fact. We see that. When a particle is in plasmoids, the energy gain rate is very low. In the what I call upstream, the region outside of plasmoids, the particles are nearly energized at the optimal rate. They're doing so by this sequence of alternating Larmor orbits in the alternating magnetic field, nearly aligned with the electric field. Now, you can, sort of like in a Fokker-Planck formalism, you would say that this gives a power law where the power law slope is the ratio for any accelerator of the acceleration time and the escape time. So the acceleration time can be measured, is the energy divided by the rate at which it's gaining energy. The escape time in this picture is the time it spends in the upstream region outside of plasmoids before either it gets out of the system or it gets captured by a plasmoid, at which point its acceleration will end. So this holds, and we have measured this, and the two timescales are roughly comparable, which means that the slope, sorry, this is a lot of words. I have backup slides, so we can talk a little bit more about it. The slopes for the particles that are enjoying this phase of acceleration is actually -1. And it can be measured if you're asking which particles are outside of plasmoids and what's their slope. The slope is -1. But then it's not the whole particles because they're spending in this phase a very short amount of time. Most of them, they're trapped in plasmoids. And then it's a balance between the rate of particle advected out of the system and the rate at which the particles get from the phase of active acceleration to the phase of passive acceleration. And one time scale, the advection is energy independent. The other one depends on energy. So you steepen the slope by a factor of 1 more power of gamma, and you get gamma to the -2. Now, what is really missing here is why these two time scales are comparable. They're measured to be comparable, but is there something more fundamental for why they're comparable? And I don't know yet. It was a long answer, sorry. Okay, what can we do with it? Okay, I built this framework, an understanding of particle acceleration in reconnection, to explain something about high energy astrophysical systems. And first, the question you should be asking yourself is where reconnection happens in astrophysical systems. So this is a very detailed picture of processes that are happening. I won't go through it, of processes that are happening near a black hole. And all of the sort of like cycle of energy exchanges that you have in this system. So this was overly complicated for me. I asked my daughter to color this in some meaningful way. This is what she came up with. And clearly you can see now the accretion flow, the wind, the jet, and the jet is blue, the wind is yellow, so the boundary needs to be green, the black hole needs to be black. And then I added, she didn't know, I added the magnetospheric current sheet, which I think was brought to full fruition in Princeton by Bart Ripperda and others. So at least you have the magnetospheric current sheet, but not only. It's definitely a site for reconnection, especially in the so-called MAD state. This is a state in which the black hole gets piled with a lot of magnetic flux brought by the accretion flow to the point that it cannot handle it anymore, and it goes through an eruptive phase, bringing the flux outside through a reconnection episode. This is what MAD eruptions are. I will not be focusing on this. Rather, I'll be focusing on the jet boundary, as my title said. It's revealed here already in temperature as a potential site of dissipation. Temperature is a statement about the fact that particles are hotter. And I will convince you that reconnection has a major role in energizing the particles there and heating up the plasma there. And then some unspecified corona, which will be the last part of my presentation. I don't have an arrow because I don't know where to point it, but this is what I'm going to focus on. And then hopefully I'll convince you of maybe one potential candidate for corona. So jet boundaries. So let's start from the boundary of MET7 jet, and the observational motivation for doing this work is to look at the fact and to realize the fact that the boundaries are brighter than the core. And they're brighter actually by more than just a projection effect. So what can cause dissipation there? There is one obvious candidate, which is the fact that there exists a shear flow between the inner part of the jet, which are moving relativistically, and the outer wind, which is moving non-relativistically. So that velocity shear might be giving rise to Kelvin-Helmholtz type instabilities. Is this true? At least it's true as long as GRMHD simulations seem to confirm this. This is done by Jordi, and it shows the presence of those curly vortices at the outskirts of a black hole jet that very much resemble our mental picture of Kelvin-Helmholtz type vortices roll up. What is the nonlinear stage of these instabilities? Can we do anything useful in terms of particle acceleration and emission? So we set to study this in an oversimplified way. The jet here is a patch of plasma that moves up at relativistic velocities, surrounded by a medium that is not moving. What's shown here is the magnetic field. Most of the magnetic field is actually out of the page. The jet is electron-positron. The ambient medium is an electron-ion plasma. And we see how it behaves for conditions that are as close as possible to the boundary expected in realistic black hole jets. So this is how the system evolves, and it is showing indeed results from Kelvin-Helmholtz type instabilities. This might be a little bit, I think, novel in the sense that this is a realization that is a kinetic simulation. So a kinetic simulation has to resolve small scales, but the statement here is just that we are resolving dynamics that is happening on scales large enough that the fluid approach, MHD-like, applies. So the same growth rate that we measure actually in PIC here is predicted by MHD linear theory. The nonlinear evolution, it's the reason why we're doing a simulation, and that's the interesting bit. So the reconnection aspect of the story is the fact that these vortices in their nonlinear stages are rolling up onto themselves. So the magnetic field lines here in white, pointing up initially, come back, and you have this anti-parallel configuration, which is what I've been postulating about so far in terms of efficient dissipation by magnetic reconnection. So reconnection is a natural byproduct of the nonlinear stages of Kelvin-Helmholtz evolution. It brings together efficient particle energization. This is the particle spectrum, so how many particles you have as a function of kinetic energy. The movie will run again. You will see that the largest evolution in the particle spectrum is happening indeed during the nonlinear stages of the Kelvin-Helmholtz, which is exactly when reconnection is a major ingredient of the evolution. So reconnection accelerates particles in the nonlinear stages of the Kelvin-Helmholtz. Yes, Marcus.
Based on what you said at the beginning of the talk, one should know the afterglow equals 2 or close to 2.
The afterglow has nothing to do with reconnection. The afterglow is definitely a shock, and particle acceleration at that shock is purely shock physics, unmagnetized even, or very weakly magnetized. The ratio of the magnetic energy density to the rest mass energy or to the pointing flux into the shock over the kinetic energy flux is very low. So it's unlikely that reconnection has any role in that. It's always good to think about energy scales. These are systems in which you are leveraging onto the fact that you have more energy in magnetic fields than rest mass. Afterglows, opposite case. You have much more energy in the flows, and you should use that for acceleration. Yes, Sasha. Yes, but it's not the only field. So here you have both. What I would say it's a poloidal field in the page and a toroidal field. This is language for jets. And if you were to have just a poloidal field, the flow will be stable because of magnetic tension, because it's so strong, the magnetic field, that it can stabilize it. But for I would say a relatively wide range of angles, from 20, 40 degrees up, the pressure that the out-of-plane magnetic field provides is enough to compensate for the magnetic tension. The system finds a k-vector of instability. Yes. Let me expand a little bit more on that, and then if I'm not answering, please ask again. The short answer is that spectrum is only for the jet particles. There are very little particles from the wind that are able to get energized. And you can kind of see why, because it's ultimately a current sheet or a reconnection layer that is formed by jet material coming up onto itself. So the amount of wind material that we're bringing into the acceleration region is very limited. This is the trajectory of one particle. I'll skip the second phase of acceleration. I just want to emphasize this first phase. The energy of the particle is the black solid line. The dashed red line is the work done by the parallel component of the electric field. So if you remember what I told you before, the first stages of energization from reconnection, and this is the case of a strong guide field regime, effectively rely on the work done by the parallel electric field. And the fact that the two lines track each other in this early regime is a signature of reconnection physics, is the reason for the particles accelerated at this stage. And in fact, the particle is on top of a current sheet and many other evidence. I'll skip the second part of the story for time reason, but you can ask me later. So the basic conclusion from this topic is we started from a motivation, limb-brightened emission of relativistic jets, AGN jets, Kelvin-Helmholtz and ensuing reconnection and resulting reconnection can accelerate particles and explain that. You also have a structure in the jet that is formed in the nonlinear stages of evolution. The core of the jet retains its relativistic Lorentz factor. The sheath or the boundary is now transrelativistic. And this is often used without knowing the physical reason in modeling of emission from AGN jets. And finally, and this is work that Jordi has done, polarization receives significant consequences from the presence of this Kelvin-Helmholtz type vortices on the surface of the jet, on the edges of the jet, to the point that since it's more messy than for a laminar jet, the polarization signal will be degraded, and you generally result in depolarization as compared to the case of a laminar jet. And hopefully we can get to the stage with next generation EHT in which some of these aspects may be observable. I promised you something about coronae, and I'm going to fulfill my promise in the remainder of the talk. So what is reconnection in black hole coronae, and actually even more fundamentally, what are black hole coronae? The motivation here is for a system in which the black hole is accreting from a companion star. This is an artist's depiction. This is your star, creates an accretion disk. The jet is a plus. The physical question is on the right here. We're trying to understand the so-called hard state of the systems of these X-ray binaries. The soft state can be understood from a simple Shakura-Sunyaev accretion disk model. It peaks at 1 keV, roughly speaking, which is exactly the temperature you would expect from the inner disk. But the hard state with a peak in photon spectrum at 100 keV is a mystery. And the usual interpretation is that the disk photons, soft disk photons, are upscattered, Comptonized by some coronal electrons. The coronal electrons are somehow kept hot by some often unspecified heating mechanism to the point that it can retain 100 keV temperatures despite the fact that you have a lot of photons around, and so these electrons are continuously subject to significant Compton losses. This is the standard model. And then you should really ask, what is the candidate mechanism that can keep the electrons as hot as 100 keV temperatures? And reconnection, not even reconnection can do it. Reconnection cannot energize the electrons fast enough, or at least the bulk of the electrons fast enough such that they keep 100 keV temperatures in these systems flooded with many photons and so prone to significant inverse Compton losses. Cooling time is just so much shorter than dynamical time that you cannot release enough energy to offset the cooling losses. So, but thermal motions are not the only motions you have. This is sort of like a 101 description of thermal versus bulk. Thermal motions, internal, random, which are temperature, versus ordered motions, which are bulk. And bulk motions are perfectly fine in Comptonizing as well. You just need to have them on the right energy scales. It is much easier for inverse Compton cooling to kill internal random motions rather than bulk motions, especially if the bulk motions are constantly pumped, constantly driven. I'm anticipating what's going to come next. Question is, what is providing those ordered bulk motions? And now reconnection can do it. You need now discrete structures that are moving, organized, and this is exactly what the reconnection plasmoids do. Flux ropes, plasmoids, magnetic islands, those structures that we have seen since the early slides that are a natural byproduct of reconnection are indeed capable of carrying bulk motions. Are the bulk motions of the right energy scale to produce Comptonized emission? This is going to be the topic of the next couple of slides. This is now a simulation that is including radiative losses, Compton losses, quantified by this equality. This equality defines a characteristic Lorentz factor at which the cooling losses equate the accelerating power of the electric field, or the loss power is equal to the accelerating power of the electric field. So a low value for this gamma rad or gamma critical parameter means you're cooling a lot. In the case of no cooling, you have gamma critical equal infinity. There are two more panels that will be showing up here and that are going to prove that bulk motions control most of the Compton signature in this system. This is the Compton emissivity accounting for all types of particle motions, temperature, bulk, ordered bulk, all included. The final panel is only accounting for bulk motions. If you don't see much difference, it's because I don't see much difference as well. And that's because most of the Comptonization, in this case of strong cooling, is not done by temperature effects, but it's done by ordered bulk motion effects. We can be a little bit more quantitative. This is now the particle spectrum in the case of strong cooling. So again, number of particles, particle energy. The particle spectrum accounting for all motions is the blue, dark blue. Bulk motions only is the cyan, and you see that at the peak, which means where most of the particles are, the two lines are hardly distinguishable. Most of the motions are in bulk motions. Even more surprising, they don't look very different than a Maxwellian. So a Maxwellian distribution with a temperature, and I stress temperature, of 100 keV is what's used in standard models for Comptonization. Now, the energy here is still over 100 keV. It's not temperature. It comes from ordered bulk motions, but it can be still described with some effective temperature, which is just a statement about typical energy, of 100 keV. So typical bulk motions in reconnection have the right energy scale to produce Comptonized emission with the properties that we measure. We can be going one step further. These are now photons that are being tracked through the kinetic simulation and to produce an observed spectrum with an optical depth of order unity, which is typically what's inferred from black hole systems, from X-ray binaries, and a magnetization of 3. This is a case of an electron ion plasma. The spectrum that we produce from the simulation, the dashed line, matches the observations very well. So reconnection, even though it does not rely on thermal effects, can produce bulk motions, which are perfectly fine for Comptonization and to explain the hard X-ray emission of black hole binaries. In the last 10 minutes, maybe even less, 7 minutes, this is what we had until 1.5 years ago. It's a sketch. Okay? I argued that reconnection may be powering this emission, but where this reconnection layer is as compared to the black hole global environment, I couldn't say. Okay? In some sense, the corona is what my daughter would call a unicorn, which we can kind of infer properties of, optical depth, typical energy, but we really don't know the exact shape, where it is, whether it flies or does not fly, whether it moves, does not move. So where is the corona? I'm not going to be that bold, especially with Jim being here. I'm going to ask, where is a potential corona? And the insight here has been provided recently by global GR MHD simulations, including radiation, that are showing that in the presence of a significant, if the accretion flow is initialized with some significant magnetic flux, the flow transitions from outer radii, thin disk, cold, dense, to inner radii in which the disk is thicker, or the flow is thicker, more dilute, hotter, piled up and threaded with significant magnetic flux. So in some sense, the inner region is not very different than a mad flow, than a magnetically arrested disk that I argued before as the origin of the magnetospheric current sheet, among other things. So we can now zoom into the inner regions and ask, what are the properties of mad accretion flows that might be conducive to efficient Comptonization? So this is now a zoom in of a mad flow. It's even 2D. So this is really sort of like not state of the art from the point of view of MHD, but we're trying to quantify as much as possible the physical properties of this system. I'll let the movie run. The left shows the gas to magnetic pressure ratio. The right shows basically the magnetic to rest mass ratio. And one thing that you should see is that the jet boundary is not boring at all. And it shows at relatively many times occurrences of blobs that are reconnection plasmoids. So plasmoids in copious numbers exist at the jet boundary. The jet boundary is a very active region. If reconnection is happening there, lots of dissipation will be happening there because reconnection is an efficient way of dissipating the energy. We can restrict ourselves to the jet boundary, and we identify the jet boundary with two cuts of the quantities that I just mentioned, the gas to magnetic pressure ratio larger than 0.1, and at the same time, the magnetization, magnetic to rest mass energy ratio larger than 0.15. You can see that you can reasonably identify the jet boundary at that point. This is what the color means. So color at zeroth order means you're getting the right region, but at second order, this is the bulk Lorentz factor squared minus 1. This is exactly what should enter the Compton power. And you see that it's of order 1. So trans-relativistic motions at the jet boundary. This is coming back to what I already said before. The jet boundary is hosting some trans-relativistic bulk motions. There are two properties at zeroth order that are needed for this to be a viable mechanism for the corona. Number one, it needs to carry a lot of energy, and the jet boundary is actually the location where with the largest electromagnetic flux. Not the jet core, but the jet boundary actually carries even more power than the jet core, comparable to the overall accretion power. This is needed for the coronal emission. Number two, as I argued already, you need a characteristic energy to be just the right energy. So we measure these bulk motions, and we can produce a spectrum of the bulk motions as a function of the bulk Lorentz factor. So these are just bulk motions in the jet boundary, and they can be fit with an effective temperature of over 100 keV, which is, again, the right energy scale for efficient Comptonization. Are we done? Not yet. if we identified this unicorn, there are at least 3 more things that need to do, which we have to do, but hopefully next year we'll bring them. We need to compute the spectrum self-consistently by tracing photons through the global evolution of the system. Polarization is key. We have beautiful results from IXPE that are actually challenging most models for where the corona may be or what the corona is. And finally, calculating timing signatures. All of them can be done in a global scenario, and hopefully we will be able to see where this unicorn is, or at least where one unicorn is. With that, I'll conclude. As you might have realized, I have not discussed neutrinos, even though I promised I was going to say something about neutrinos, but then I realized I was going to just say too much. So I'm happy to address neutrinos in the question time, but I'll leave you with my questions, and thank you again for your attention.
On the precise mechanism that accelerates particles in the presence of plasmoids. In the 2D picture originally, it was that these islands are quasi-elliptical, and the process of contraction circularizes them and releases energy. That is energetically favorable, and a process of Fermi acceleration then, back and forth, is the mechanism for energization in 2D. If you have a 3D component, you will generally break those islands. Field lines will stochasticize. So this picture then needs to be resurrected with some memory, if you will, of what is then causing this Fermi acceleration. You made a comment during your talk that you thought that if the particles get trapped in plasmoids, they're no longer energized. And this puzzled me because this is in contradiction to the original picture of the reflection due to Fermi. What is operative in 2D and in 3D according to you?
So let me make a very critical distinction between electrons in non-relativistic reconnection and whatever species in relativistic reconnection. The relativistic case, everything goes at the speed of light, which means both the particles and the merging islands. Or if you think about it as like the contracting islands at early time, but more generally at later times, you have this process when 2 islands merge, and then they become from oval to spherical or circular. This merging is happening at a fair fraction of the speed of light. No particle has enough time to go around more than maybe half an orbit or maybe one entire orbit. So this idea that this is a continuous process in which you can have many circles around the core of the island is a peculiarity of having fast electrons in an otherwise slower system because it's evolving on the Alfvén speed of the flow, which is the Alfvén speed of the ions. So I think that that's a qualitative distinction that needs to be made between the relativistic case and the non-relativistic case. Now, there are more subtle differences related to the fact that this process should be operating. However, it does operate only when mergers are happening. And mergers don't happen all the time. Most of the time, the plasmoids are actually sitting there accreting magnetic flux, but without major mergers happening. And this process of accreting magnetic flux is piling up the flux, piling up the magnetic field, causing the magnetic field to increase. And this is why I said, like, the particles, even in an isolated plasmoid, in the absence of mergers, can get energized even in 2D, but relatively slowly as the square root of time, because the magnetic field increases like linearly with time, and the magnetic moment is conserved. So there are sort of like a duty cycles issues on this process that I have a little bit of a hard time sort of like believing it fundamentally as a general process for the relativistic case. But I think the zeroth order difference is just that everything moves at the speed of light. So the plasmoid merger happens within 2 light crossing times. The particles don't have a lot of time to experience this convergence of the flows.
In the reconnection at the jet boundaries, is there a limit to the particle energy set by the amount of flux available in these vortices to reconnect?
It's a great question, actually, and that's tapping exactly into our ignorance. So the way I see this process now is that reconnection is convincingly providing the first stages of energization. The particles are so tightly bound to the field lines before energization happens that they cannot even sample the larger scale velocity shear, which could in principle provide channels for energization. So reconnection can serve as an injection episode, and maybe to accelerate them a little bit more, such that their Larmor radius at that point, and this is the part that I skipped, becomes comparable to some scale where they can appreciate the velocity gradient. And at that point, another channel for energization can pick up, which in this case will be shear-driven acceleration. It's basically, for everyone, it's basically the same as Fermi acceleration. Fermi acceleration relies on the convergence of flows at a shock. This one still relies on gradients in the velocity flow, but the gradient is perpendicular to the velocity. But it's basically a form of Fermi acceleration. Where this transition happens, it's still a major question mark. Whether reconnection can only give you up to sigma, let's say, and then you need to rely on something else, or whether reconnection can give you significantly beyond sigma, and then at some later stage, unspecified, a different acceleration channel picks up. And that's because of limited dynamic range. We don't have a dynamic range capable of seeing a lot of dynamics beyond gamma equals sigma in reconnection within a larger environment in which free energy is provided by other channels, in this case, the shear in the velocity. It's a great question.
That sort of observational question, Lorenzo. Looking at this little guy figure of the jet, I clearly see the double spiral structure here, which goes pretty much to the radial core. It's like there is the explanation within your framework for what the double structure is. Like this.
Here, this one.
Yes, this.
Not obviously. Not obviously. It needs to be a global question, and I am not sure I have an obvious answer.
That's one Marcus mentioned.
Oh, okay. Is there a connection between the magnetic field ratios, the guide field to the reconnecting field, and how much dissipation you get, or the efficiency of dissipation?
Yes. Yes. So there are two aspects of this question. If you're adding a guide field, which is non-dissipative, then if you're asking how much of the overall magnetic energy gets dissipated, of course it's going to be smaller because the component that can dissipate is just a fraction of it. But in relativistic reconnection, that's also a relativistic peculiarity, the guide field is actually inhibiting the reconnection process. The dynamics of reconnection is slower in the presence of a guide field, so the rate at which you're dissipating is also lower. So it's not just a question of like overall the energy in the dissipative, in potentially dissipative component is lower because some of that is locked in the guide field, but also even the amount of that energy that can get dissipated within a given amount of time is lower. And that's because the guide field is effectively acting as mass, inertia. And that just makes things slow down. So you're making your structures heavier by the energy density of the guide field.
The last question.
It's probably very turbulent as well, and there's models for turbulent comptonization. And also, I think you might have done as well. I mean, do you now favor plasmoid motion as being the bulk comptonization mechanism as opposed to turbulence and flow?
Yeah, I think we're trying to unveil pieces of a unicorn. So I think what I can honestly say is that the jet boundary does show episodes of reconnection. And whether the comptonization is happening in the turbulent motions of the plasmoids themselves, and whether this can be described as turbulence in itself or as a different stochastical variation. It is still stochastic, but it's not, let's say, homogeneous and isotropic turbulence, I cannot say. It is clearly, and that's an absolutely fair point, if this is one potential candidate for the corona, it's not a single, well-defined, perfectly isolated reconnection layer. It is a mess in scientific terms. Yeah, but whether this is genuine turbulence as we have learned over the years to be, or it's a variant of turbulence that whose biggest structures are reconnection dominated. We work under the evidence that such structures, reconnection related, exist, whether the framework could be cast as equivalently as like a turbulent Comptonization, possibly.
Okay, there are 2 spots I think left for Institute members for dinner, so please sign up for those. Let's thank Lorenzo again.
Thank you.